So in this video, I'm going to introduce Chapter 3, which covers acid-base equilibria. And what we'll do is we'll use these chemical concepts and apply them to natural waters and try to understand what type of chemical processes affect pH and the composition of natural waters. And so many of these processes are large scale, they're geochemical, they're geobiological. And so the main process is that of erosion, where the water cycle dissolves the continent and that material is transported to the bottom of the oceans. So this process, the water cycle, eroding the continents, this is one giant acid-base reaction. So this is going on constantly and has been going on for billions of years, and it's continual. And the main acid we're talking about is CO2. When CO2 dissolves in water, in rainwater, it forms a slightly acidic solution containing carbonic acid. Other metals can also behave like acids. We'll talk about that later, but they can also affect the pH of water. The bases, well, the base is the continent. It is the rocks and the minerals. A lot of the constituents in the continental rock, such as silicate and carbonate, these chemical species, they behave like bases. And so these two things come together during precipitation over land, and this process is responsible for the composition of the ocean and also the composition of all natural waters. And so let's look at some of the basic terms in this chapter. First thing is let's define acid and let's define base. And so if we go back about 125 years, Arrhenius was the first one to define what an acid and base is. He said that an acid is H+, and a base is hydroxide. Well, that's a very simple definition, and it works much of the time, but what we actually need is something a little bit more broad. And the Bronsted-Lowry definition, again, probably have to go back 100 years. This is a much more flexible definition. It's very similar, but it allows for more things to be acids and bases. And so an acid is an H+ donor. So it's not much different than the first definition, but this allows for, say, organic molecules or macromolecules in a biological system to donate a proton. H+ comes off the molecule. That is now considered an acid. And for a base, anything that accepts that proton is now a base. So it's not just OH- hydroxide accepting a hydrogen plus to make water. Now it's any molecule that accepts a proton. So now we can consider silicate and carbonate as a base. So we've defined what an acid and a base is. Now there are two types of acids and bases. So the first type is strong acids. Now we're not going to talk too much about strong acids and bases because they're not very common in natural systems. And it's a good thing because these types of acids and bases have a very dramatic effect on changing the pH of water, which is very hard on biological systems. And so what makes an acid or base strong is that they dissociate completely when they are added to water. So when you add hydrochloric acid to water, it does not stay in the form of HCl. All of it, essentially all of it, turns into H+. And so this H+ contributes to the change in pH. Same goes for a strong base like sodium hydroxide. It does not stay in this form of sodium hydroxide when added to water. It completely dissociates, and this hydroxide will make the solution very basic. And that's going to be very different than what we see in natural waters, natural systems. So an example of a strong acid in nature, well, you kind of have to go to human activities, things like acid rain from, say, smokestacks that exhaust and fumes reacting with the atmosphere, oxygen, and water to create strong acids, such as sulfuric acid is a constituent in acid rain, or nitric acid. Again, after reacting with water and oxygen, these pollutants like NOx and SO2, they slowly convert to these strong acids. Also, mine drainage, opening up bare bedrock like that. Some of the minerals, especially sulfur type minerals, create conditions along with biology to produce very low pHs, even negative pHs. So very, very detrimental to the aquatic environment. In terms of strong bases, they're hard to find in natural systems, but caustic water is the closest thing. Mono Lake is pH 10, fairly caustic. It has a lot of different bases in it, things like carbonate and such, but it does have about 4 ppm sodium hydroxide. So these are strong acids and bases. What we're more interested in are the weak acids and weak bases. These acids and bases, these weak species, they're the ones that control and regulate the pH in natural waters. So let's first talk about weak acids. So what makes a weak acid? They dissociate sparingly. So doesn't mean they're better or worse in terms of, say, being dangerous to us when we work with them in the laboratory. But weak acids, in terms of the term weak, all it means is that they dissociate sparingly. So note now, rather than showing that this weak acid, which I'm going to give the symbol HA, H here is the proton, the acidic proton, and that's going to be donated. A can be anything. A can be anything. So there's lots and lots of different weak acids. And so this weak acid is going to dissociate sparingly. And that's why I have the double arrow, because we're going to actually set up an equilibrium between the reactants and the products, because there's actually going to be quite a bit of this in solution at equilibrium. And so when you add a weak acid to water, water behaves like a base. How does it behave like a base? Well, it accepts a proton. That's the Bronsted-Lowry definition of a base. And when it accepts the proton from the acid, it makes hydronium ion. And we call that an acid-base pair. This is a little technical, more than maybe you'll be tested on, but you should know that these two are paired. This is a base to this acid, and same goes here. My weak acid has a conjugate base as well. It has its pair, it's A minus. And so this is a base, and depending upon the shift in this equilibrium, we may go and shift this way and make the weak acid again if we added, say, some H plus to solution. And just note, if you've never seen the hydronium ion, it's just aqueous H plus. So it's water plus a hydrogen ion attached. So they are the same thing. Also, talking about the same thing, we could write the dissociation of an acid like this. And so this equation here says the same thing. And it shows that the weak acid dissociates into H plus and A minus. So what I would like you to be able to do is write an equation expressing the dissociation of a weak acid. Either of these would work. And I would also, for that equation, would want you to be able to write the equilibrium expression. So let's look at an example of a weak acid. The weak acid that we will primarily study is that of carbonic acid. Carbonic acid is essentially aqueous CO2. This is how we express aqueous CO2 in solution as carbonic acid. And carbonic acid is formed by the CO2 in the atmosphere dissolving in water, and it is in equilibrium with this carbonic acid. And this is happening constantly in rainwater. You know, rainwater is saturated with CO2. So once the CO2 is in solution, dissolved, it will react with water. Water will behave as a base. It will accept a proton. It will form the hydronium ion. And that leaves me bicarbonate. Bicarbonate in this reaction is a base. It is the base to carbonic acid. And we can write the equilibrium expression for this reaction. So note here, if I added H plus to this system, what would happen to the equilibrium? How would it shift? Well, if I added H plus to this system, it would shift to the left. And what would happen is the bicarbonate would convert back to carbonic acid. And so in doing so, the H plus reacts with bicarbonate and disappears. It doesn't contribute to the pH as if we added it to pure water. So that's just a side note. I want you to think about that idea, because this is going to become important as to why we're interested in studying weak acids and bases. And the reason for that is because they help regulate the pH, buffer the system, because they can absorb H plus and hydroxide if added to the system. Well, let's take our bicarbonate and treat it as an acid. It has a proton that can be donated. It has an acidic proton. And so here it behaved like a base, but now carbonic acid is going to react with water, which is a base in this reaction. It's a base. And it's going to form carbonate and more hydronium ion. And so again, it donated its proton, the definition of a weak acid, and it does it sparingly, of course, forms carbonate and H+. And I would want you to be able to write that equation along with the equilibrium expression. There are other examples of weak acids in natural waters. Here are just a couple. Humic acids, fulvic acids. You've probably heard of tannins, the substances in teas and such, tannic acids. All these are organic acids. And, you know, for example, humic acid, this is just a proposed structure. Humic acids are a class of molecules. They look all different. I imagine them as somewhat like snowflakes, where each molecule is a little bit different, but they're degradation products of the decomposition of lignin. And so they all look different. Bacteria chew up the lignin in the cell walls of plants, and they use some of the chemical energy for their metabolism, but they kind of leave around these humic and fulvic acids. And so these hydrogens here on what we call functional groups, this is like a carboxylic acid, but these hydrogens, this is a phenolic group, and there's other groups as well, but these hydrogens are acidic. They will pop off and go into solution and leave, if it comes off, it would leave a negative charge on the molecule. And so these molecules, again, are affected by pH, and if in the solution at high enough concentration, can help slightly buffer the system. So weak bases. Let's look at bases really quickly. We're going to do the same type of thing that we did with weak acids. So in this case, a base protonates, meaning it accepts a proton. And a weak base does this very sparingly, such that the base itself is present in solution, but a very slight amount of it will accept an H+. So again, this is a pair. This is an acid-base pair. And notice too, this time, water behaved like an acid. So water can behave like an acid or a base. It's amphiprotic, they say. And so to consider what's going on here, just note that whether you're an acid or a base, it's all relative. It's all relative to who you are reacting with. So you should be able to write a reaction showing the protonation of a base, reacting with water to form the protonated form of the base, and you're left with hydroxide. So this affects the pH of the solution. You should again be able to write the equilibrium expression for this equation. And for example, let's look at carbonate. There's a lot of carbonate in natural waters because it's in equilibrium with calcium and magnesium carbonate minerals that are in the sediment and also in the exoskeletons of organisms like corals and seashells. Well, it reacts with water to form bicarbonate. So this is an acid-base pair. Carbonate accepted a proton to form bicarbonate. So this is the acid, carbonate's the base, and in this reaction, we form hydroxide. So it's following this template up here where B is carbonate, CO3 2 minus, and BH plus is bicarbonate. So we can write the equilibrium expression for the protonation of the base. That's what the B stands for, is that this is an equilibrium constant for the protonation of a weak base. And we could do this again. We could treat bicarbonate as a base, react it with water, and form carbonic acid. Now this template here is the only way to express the protonation of a base in water. Remember that in weak acids, I showed you two ways to do it. Bases only have the one way. You have to react with water to understand how the base creates the hydroxide, which changes the pH. And so this figure is from your book. It shows quite a few different bases that occur in oxic waters, so in waters that contain oxygen. And here's a couple that are present in anoxic waters, such as the Black Sea, the deep waters, at least, of the Black Sea. But note, too, getting back to the beginning slide about this gigantic acid-base reaction, note how the freshwater systems contain different amounts of these bases compared to seawater. And we could talk a lot about why we're getting these changes, say in carbonate, in freshwater, and then an increase in deep water, in the seawater. Same with borate. Borate is a lot more concentrated in seawater than in freshwater. But we will leave that for another lecture. Or you can ask questions about that the next time we meet. But just note that these bases are important in natural waters. In acidified waters, they will become protonated and become actually weak acids. And last, here are some reactions that occur in natural waters. And these are all equations written as acid dissociations. So we're looking at Ka values. These are Ka values. There's a few in here that are just showing the, say, a gas dissolving. But most of these that have the H pluses, these are K values for the dissociation of a weak acid. Water itself does its own dissociation. And so what this figure from your textbook shows is, again, that we need to consider ionic strength. We've covered that in chapter 2. Ionic strength does affect the value of the K value, the equilibrium constant. And so we will be thinking about that when we look at acid-base equilibria in the ocean. Lastly, I'm introducing this table because we are also going to start thinking in terms of pKa values. So pKa values, all that means is we take the negative log of the equilibrium constant. That allows us to get these nice, round numbers, these general numbers that are much easier for us to process and interpret. And so we're going to use pKa's to show, say, how ionic strength makes the pKa smaller. And that will help us understand how it's going to shift the pH and things like that. So biochemists, even geologists, I believe, use a lot of pKa K values or take the negative log of a lot of values to make things a lot easier to um, to digest. And of course, pH in itself, why do we take the negative log of the hydrogen ion concentration? Well, it's much nicer to and easier to say that a pH change from, say, 7 to 8 rather than to say it changed from 1 times 10 to the negative 7 to 1 times 10 to the negative 8. So I think that must make sense to you. Working on a log scale sometimes is very beneficial. So I hope this video helps with the terminology on this topic, and please watch this along with part 2, which is posted on YouTube.